Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we will see the problems on auto power spectral density. So at the end of this particular session, student will be able to learn the definition, mathematical definition of auto power spectral density, and also we will define all the properties of auto power spectral density. We will apply those concepts in solving the real-time problem. So we know that the power spectral density is nothing but how much power a random signal is distributed over different frequency components. The power of the random signal is distributed over different frequency component is given by the power spectral density. So the power spectral density is mathematically defined in two ways. One definition is, in general, the power spectral density definition is given as limit t tends to infinity expectation of xt of omega whole square by 2t, where xt of omega is nothing but the Fourier transform of the random process, which is restricted over the interval minus t to t. And another way or alternate way of computing the power spectral density is the power spectral density and autocorrelation function are the Fourier transform base. So we use this relation in solving the problems. Instead of this definition, we will use this definition quite regularly in solving the problems, because the Fourier transform concept will be used, which will be very useful in solving the answers. And if you want to compute the average power can be computed in two ways. The average power can be computed using the general formula, or the average power can be computed in another way is, if autocorrelation function is given to us, autocorrelation function at tau is equal to 0 gives you the average power. Otherwise, the average power also can be computed using the power spectral density. Integrating the power spectral density over a predefined bandwidth, we will get the average power. So this we will use in computing the average power. So first we will recall the properties of the power spectral density, which will be helpful in solving the problems. For a wide and stationary random process, the power spectral density is always a positive quantity. So the power spectral density always provides a positive value. And the power spectral density at origin is mathematically equal to the area under autocorrelation function. And power spectral density is also an even function of omega. Power spectral density is always a real function. Next, the time average of mean square value of wide and stationary random process is also equal to area under power spectral density. That is nothing but average power can be calculated using this property. The power spectral density of derivative of the random process is also equal to omega square into sxx of omega. And the last relation, which is very important relation in solving the problems, Wiener-Kinchy relation. So this Wiener-Kinchy relation is quite useful in solving the problems. The Fourier transform of autocorrelation function is power spectral density, or the inverse Fourier transform of power spectral density is correlation function. Let us solve one problem which is related to the power spectral density. Autocorrelation function is given and we are asked to compute the power spectral density. So the autocorrelation function Fourier transform gives the power spectral density. So we are applying the Fourier transform formula. So sxx of omega is nothing but the Fourier transform of the autocorrelation function, rxx of tau e power minus j omega tau d tau. So we will apply this formula. So given minus infinity to infinity, a e power minus b absolute value of tau. We know that the absolute value of tau is equal to tau when tau is greater than 0 and is equal to minus tau when tau is less than 0. When tau is less than 0, the range will be minus infinity to 0. When tau is greater than 0, 0 to infinity. 0 to infinity, it is plus tau. Minus infinity to 0, it is minus tau. And e power a and e power b can be written as e power a plus b. And integration of e power at is e power at by a. Substituting the limits and finally simplifying, we will get 2ab by omega square plus b square. This is the power spectral density when autocorrelation function is given to us. We used the concept of Fourier transform. Next, a circuit is given to us which is a combination of RC elements. Now what is here we are doing is, we are applying an input and whose autocorrelation function is rxx of tau. Now they are asking us to compute Sxx of omega and Syy of omega. So given Rxx of tau, we can compute Sxx of omega using the Wiener-Kinchy relation. The Fourier transform of this function gives us Sxx of omega. So that is, we know that the e power minus a absolute value of tau, the Fourier transform pair is a by omega square plus a square, 2a by omega square by a square. So we use that relation, we will get 4 by 4 plus omega square. In order to compute the output power spectral density, input power spectral density and output power spectral density are related using the relation output power spectral density is absolute value of transfer function whole square into Sx of omega. So for finding Syy of omega, first we need to compute the transfer function for a given network. In order to compute the transfer function for a given network, firstly we need to modify the circuit elements in terms of Fourier domain. So in Fourier domain, the resistance remains same 2 omega and 2 farad. The capacitance will be 1 by j omega c, 1 by 2 j omega. Here the capacitance is 1 farad, it will be 1 by j omega. Now the parallel combination of this impedance is computed using Z1, Z2 by Z1 plus Z2 x of. So applying that, the parallel combination of impedance is this one. Now x of y of omega is x of omega into Zc by Zp plus Zc. So doing that, and y of omega by x of omega is Zc by Zp plus Zc. The transfer function we will get is 1 plus j 4 omega by 1 plus j 6 omega. So now we know the relation, we can substitute in the relation. We know that the absolute value of a plus jb is equal to square root of a square plus b square. So applying that, 1 plus 16 omega square by 1 plus 36 omega square into 4 by omega square plus 4. So the Syy of omega can be computed using this relation. Next, another problem is given where autocorrelation function is given. Now we are asked us to compute the power spectral density. So we will use this relation, a power minus b absolute value of tau is equal to 2ab by b square plus omega square. Applying that relation, this will be equal to 2 into 3 by 3 square plus omega square, 1 square plus omega square. Next, 5 into e power minus 4 into absolute value of tau is 2 into 4 into 5 divided by omega square plus 4 square. So again, computing the LCM, the final answer will be something like this. Adding this 6 by omega square plus 1 plus 40 by omega square plus 16. So 6 omega square plus 6 into 16, 96. 96 plus 40, 136. So 46 omega square plus 136 by 1 plus omega square into 1 plus 16 plus omega square. Next one problem is given related to inverse Fourier transform pair. The power spectral density is given. Now we are asked to compute the autocorrelation function. So we will apply the inverse Fourier transform concept, and the formula for inverse Fourier transform is given here. And the limits are limited between minus k to k. The integration of e power j omega tau is e power j omega tau by j tau, substituting the limits. This is in the form of e power j theta minus e power minus j theta by 2j, which is mathematically equal to sin theta using the Euler's relation. This is a by pi tau into sin k tau. Now the power spectral density function is given to us. Now we are asked to compute the autocorrelation function on mean square value, which is nothing but average power. So the power spectral density and autocorrelation function are related in the Fourier transform pairs. What we will do is, firstly we will apply the partial fractions for power spectral density. We will split the power spectral density in a we will split into the elements so that we can apply the Fourier transform pair very easily. So, by splitting the power spectral density, by applying the partial fraction expansion, by splitting the terms, you will get 1 by omega square plus 1 plus 1 by omega square plus 9 and multiplied with some scalar elements. So, we will apply the here inverse Fourier transform concept. By applying inverse Fourier transform concept, this can be written as e power minus tau. This is written as e power minus 3 tau. So, e power minus a tau is equal to 2a by omega square plus a square. So, we will use this relation, applying this relation, this is e power minus tau, this is e power minus 3 tau. So, once the autocorrelation function is known to us, the mean square value can be computed as mean square value is expectation of x square of t is equal to autocorrelation function at 0. So, the mean square value will be minus 1 by 16 e power 0, 3 by 16 e power 0. We will get 2 by 16 which is equal to 1 by 8. So, the mean square value or average power is equal to 1 by 8 watts. And one more problem is given to compute the average power. So, average power, computing the average power, what we will do is first we will develop the autocorrelation function. Autocorrelation function at tau is equal to 0 gives us average power. Given a random process a cos omega naught t plus theta, where a omega naught are real constant, only theta is the random variable which is distributed uniformly. So, f theta of theta is equal to 1 by b minus a, that is 1 by pi by 2 minus 0, that is equal to 2 by pi over the limit 0 less than theta less than pi by 2. So, computing the average power. So, here normal formula is used or autocorrelation function at tau is equal to 0 is mathematically equal to expectation of x square of t. This formula used x square of t f theta of theta. X of t is a cos omega naught t. So, cos square theta can be written as 1 plus cos 2 theta by 2 and substituting the limits, and finally we will get a square by 2 minus a square by pi sin omega naught t. So, this parameter we can remove by computing the time average power. So, if you compute the time average power, so this parameter will not be present, because if you do the integration sin cos t minus of cos of minus t will be 0. So, this term will vanish, the residue term is a square by 2. So, the time average power is a square by 2. Next, one more problem which is related to computing the statistical parameters mean, variance and average power. The power spectral density is given. We are asked to identify the frequencies. What are the frequencies present there? So, there are different frequencies present. One frequency is omega is equal to 4. So, that frequency, we know that omega is equal to 2 pi f. The frequency will be omega by 2 pi. Omega by 2 pi. Here omega equal to 5 pi, 5 by 2. Omega is equal to 4, 4 by 2 pi, that is 2 by pi, and two frequencies are there, one frequency is 0. So, the two frequencies are computed. Next, we are asked to compute the DC power, average power. So, average power is also computed using the relation Rxx of tau is equal to 0, and the mean value is given, DC value is given as DC power is given, the DC value will be square root of 2. So, the variance is equal to expectation of x square minus expectation of x whole square. 7 minus 2, we will get 5. So, in this session what we have learned is we have defined the auto power spectral density, and we have seen the mathematical definition, and also we recall the properties of auto power spectral density, and we solved some practical problems related to auto power spectral density. Thank you.